Hello everyone. So this is a question from RE-NEET 2026. 2 moles of an ideal gas undergo free expansion from 10 liters to 100 liters at 300 Kelvin. The values of delta S system and delta S surroundings are. Okay. So R is the universal gas constant. The chapters involved is thermodynamics. Okay. So using a diagram to show what's happening, so we have a thermally insulated container. So this is thermally insulated, and there is a partition here, and here we have taken 2 moles of gas and volume is 10 liters. So here we have the gas and there is a partition, and here we have vacuum. Okay, and these things are at 300 Kelvin. Okay, and then what we do is we open the partition, that is partition is opened, and because of that the gas spreads out, and now we have 2 moles of gas obviously, but the final volume is obviously it is 100 liters. So initially it was 10 liters here. Now the total final volume is 100 liters. Okay, and the temperature is maintained at 300 Kelvin. Okay, so expansion against vacuum, so you can see this gas expanded against vacuum is known as free expansion. Okay, and since temperature remains constant, therefore delta U will be equal to 0. Okay, because internal energy for ideal gases depends only on temperature, and temperature itself is not changing, so delta U is equal to 0. And also since expansion is against vacuum, expansion is against vacuum, therefore P external will also be equal to 0. And if P external is equal to 0, we know that work will also be equal to 0, because work is equal to minus P external into dV, right? So therefore, according to the first law of thermodynamics, we know that delta U is equal to Q plus W. Delta U is 0, W is also 0. So therefore, Q is also 0. Okay, that is, there is no heat exchange between system and surrounding. Very important. No heat exchange between system and surroundings. Okay, and therefore delta S surrounding, that is entropy change of the surrounding, is equal to 0. Very important. Okay, this is because no heat is exchanged with the surrounding by the system, no heat goes out, and also no work is done on the surroundings or by the surroundings on the system. Okay, so I will write that down. Delta S of the surrounding is 0 because no heat is exchanged with surroundings and no work is done on or by the surroundings on the system. Okay, now coming back to our system, so this is our system, this container. Okay, even though there is no heat transfer, that is, no heat is going out, neither any heat is coming in, and no work is done by the system also, because we calculated that W is also equal to 0, Q is also equal to 0. Okay, but the gas spreads into a larger volume. Can you see here it was occupying a volume of 10 liter. Because I opened the partition, now it is occupying a volume of 100 liter. Okay. So because of this larger volume, this will give these molecules more space. And because of the more space, there will be higher randomness of these molecules. So therefore, entropy of the system will increase during a free expansion. Very important. Okay. So as gas spreads into a larger volume, it will lead to high randomness. Therefore, S of system will increase. Entropy of the system will increase during a free expansion. Therefore, since the entropy of the system is increasing, delta S system will be definitely greater than 0, right? So let's calculate its exact value. That is, how much is actually delta S system. Okay. Before that, we have to understand one very important thing, that expansion of an ideal gas against vacuum, that is, this particular gas expansion against vacuum, is an irreversible process. That is, I will write it down. Expansion of an ideal gas against vacuum is an irreversible process. So it is irreversible because the gas won't spontaneously or by itself return to its original chamber. Okay. So we know that delta S is equal to Q reversible by T. Okay. That is, entropy change during a process is defined as the amount of heat absorbed isothermally and reversibly. This is very important. This is heat absorbed isothermally and reversibly. Okay, divided by the absolute temperature at which heat is absorbed. Okay, so therefore the most important question is how to find Q reversible, or you can say delta S, for a process that is irreversible, because delta S is defined as Q reversible by T. Then how will we find Q reversible or delta S for a irreversible process? Because expansion of gas into vacuum, this is a irreversible process. Okay, and we cannot use this for irreversible process. This equation is valid for reversible process. Okay, so to do that we have to follow few steps. Step 1, apply first law of thermodynamics to determine the final state of the system. To determine final state of the system. Okay, so we know that delta U is equal to Q plus W, right? So we know there is no heat exchange, we know there is no work done, so delta U also will be equal to 0. So therefore T initial is 300 Kelvin initial state, V initial is 10 liters, so pressure initial will be obviously nRT by V. So this is the state 1, these are the state variables for state 1. For the final state, or you can say for state 2, T final is 300 Kelvin because we have maintained the same temperature. V final is 100 liters, and final pressure will be equal to obviously nRTF by Vf. So these are the state variables. Okay, so this is for state 2 or the final state. So now we know the initial state, now we know the final state. Okay, this is our step 1. Then step 2. Entropy is a state function, very important. Entropy is a state function. Okay, and therefore change in entropy, that is delta S, will only depend on the final and initial state. It does not matter how we reach the final state. That is, whether you are doing a reversible process or a irreversible process, we will get the same value of delta S. That is, with respect to diagram, let's say you are in an initial state and its variables are Ti, Vi, and Pi, and you reached a final state and its variables are Tf, Vf, and Pf. Okay, so it does not matter how you reach the final state. You can do a irreversible process. Let's say the actual free expansion that we are doing, in that case delta S will be equal to Sf minus Si. You can also do a reversible process to go from Si to Sf, which is the hypothetical reversible process. In that case also, delta S will be equal to Sf minus Si. So if we devise a hypothetical reversible path between the same two states, that is Ti, Vi, Pi, and Tf, Vf, Pf, it will give the same value for change in entropy. Okay, delta S will be same whether it is irreversible process or a reversible process. Okay, so actually what is happening in the irreversible process, we have a thermally insulated container with a partition initially and 10-liter volume, and it finally we open the partition and the gas spreads out. This is our irreversible process. We will imagine a hypothetical reversible process. Okay, so remove initial gas from rigid insulated chamber and place it in a cylinder of same initial volume with a massless frictionless piston. Okay, so for the hypothetical reversible process, imagine you have a cylinder with a massless frictionless piston and the volume is obviously 10 liters. Okay, and obviously we maintain temperature 300 Kelvin. Okay, so let the gas to expand isothermally and reversibly by placing this cylinder in contact with a constant temperature bath at 300 Kelvin. Okay, so we place this cylinder in a constant temperature bath of 300 Kelvin and we allow the gas inside to expand to a volume of 100 liter isothermally and reversibly, because this is the hypothetical reversible process. Okay, so therefore the piston moves outward gradually until the final volume is 100 liters. Okay, so finally the picture will look something like this. Okay, so in both situations, that is irreversible process and reversible process, the conditions are same: Ti, Vi, Pi. Here also in both situation, in the final state, the conditions are same: Tf, Vf, Pf. Okay, so for the reversible process, obviously delta U is equal to 0 as temperature is constant. Okay, we can write delta U is equal to Q reversible plus W reversible. Okay, so since this is equal to 0, therefore I can write Q reversible is equal to minus W reversible. Okay, and we know that W reversible will be equal to minus P into dV, right? So therefore Q reversible will be equal to P dV. Okay, and for ideal gases we can write PV is equal to nRT. So P will be equal to nRT by V. Okay, so I will substitute the value of P here. So Q reversible will be equal to nRT by V dV. Okay, and obviously we know the temperature is 300 Kelvin. Okay, Next step, what we have to do is, for the selected reversible path, that is this one, where the piston expands reversibly and isothermally from 10 liters to 100 liter, evaluate or calculate dq by t from initial to final. So this will give you the entropy change. Okay. So therefore delta S will be equal to, so we know what is dq or q, that is nr into 300 into dv by v, and the temperature at which we do the expansion is 300. So divided by the temperature, and integration from v initial to v final. Okay. So therefore this gets cancelled. So we are left with integration of nr dv by v from vi to vf. Okay. Remember, integration of dv by v is equal to ln v. So therefore I will write delta S of the system obviously will be equal to nr, it's a constant, it comes out from the integration, ln v, and the limits are vi, vf. Okay. So it will become nr ln vf minus ln vi. Okay. So this will become nr ln of vf divided by vi, because ln of a minus ln of b is equal to ln of a by b. Okay. And therefore delta S system will be equal to 2r ln of final volume is 100 liters, initial volume is 10 liters. So it is equal to 2r ln 10, obviously base e. To calculate ln of base e 10, we should know that ln of e, any number x, is equal to 2.303 log of 10, the same number x. Okay. So therefore ln of e10 will be equal to 2.303 log of 10, 10, and log of 10 base 10 is 1. So therefore ln of e10 is equal to 2.303. So I can insert this value here. So therefore delta S system will be equal to 2r into 2.303, which is equal to 4.606 r. Okay. So therefore the final answer is, the values of delta S system is 4.606 r, and delta S surroundings is 0. Okay. Thank you.